Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome back. In the last two lectures, we have talked about amperometric sensors. You see, when the biomolecules land on an electrode surface, it initiates a reaction that changes the current flow, and then you can detect the presence of biomolecule through that approach. Remember, this is really, we talked about really glucose sensors. And if you think about all among the sensors that are daily used, it's about 80% of the market, billions of dollars worth of sensors. It's a very important sensor, but it has an important limitations. And I'll discuss how a nanogap amperometry, especially at low concentration, how a nanogap amperometry can overcome that limits, especially the diffusion limits. So we'll start by discussing what the diffusion limit of a amperometric sensor is, explain how to improve or go around these limits by nanogap amperometry, explain how to sense DNA. We talked about glucose sensing, which is very good, but if you wanted to do DNA sequencing, especially at very low DNA concentrations, then we'll see how to use that. It's a very interesting use of amperometric sensors. Then we'll conclude. Let's quickly remind ourselves that how the glucose sensor actually worked. So the glucose sensor essentially had an amperometric sensors, electrochemical cells in the back, and then in the front end, there is a coating on this platinum electrode. And what happened, the glucose came, and the glucose oxidase essentially allowed that enzyme, the red enzymes, allowed the reaction to occur, hydrogen peroxide came out, and then correspondingly that gave up the electrons, and the current flow was detected. But if you think about the big picture, in the big picture, glucose came, and there was a current in response. Now, what happened to the glucose concentration in, let's say, in my blood report, for example, generally that I showed in the beginning of the course, generally very high. So you don't have to worry about diffusion limits and other things. So in that case, life was simple. Only thing we focused on was that how many glucose molecule is there and how much current flowed. And we saw that there's a 1-to-1 relationship. So this is sort of the equivalent picture then. We have an analyte coming in, a bunch of enzymes which facilitates the reaction, recognizes the specific analyte we are after, and a product diffuses out, and the current flows. This is the basic picture of all amperometric detection, all amperometric sensors. So now we can think about these basic pictures and see how it would be modified when the analyte concentration is extremely low. Let's say picomolar or a femtomolar. How would things change in that case? So the way things would change is that, remember, there was this redox reaction going on, reduction oxidation reaction going on a particular electrode. This is, let's say, the platinum working electrode. The other electrode I'm not showing here. And then as a result, there was a net current flow. Now, of course, if the concentration is very low, then what will happen is that the molecules will essentially diffuse towards the electrode. And this is the bulk concentration. If you wait longer and longer, then this initially it will be certain value, then it will be longer, and it will go as square root of dt. You may remember from the first set of lectures that anytime you have low analyte concentration, the depletion goes as square root of dt. So this will go as square root of dt. And the total flux will be proportional to this, slope of this concentration profile. Now this time around, what is special is that now you have also a product. Initially, we didn't have a product. Molecules came in and essentially was captured by the sensor surface. That's how what we assume. But here you see there will be this oxidized product, and the product will also have to diffuse away. Because if it doesn't diffuse away fast enough, then there will be a reverse reaction. And you may remember that that was the essence of this Butler-Volmer equation. So you see rho SR, this is the surface concentration of the reduced species. Kf is the reaction rate. So this part without the second term is just fine. It says that whatever flux is coming in, current is proportional to that. No problem. The problem is that there is also a negative term associated with the oxidized product. And so therefore, what happens that if you don't move it fast enough, if the concentration builds up, the pink concentration builds up, it will drive a reverse reaction. And the reverse reaction will subtract from the current and your current sensitivity will go down. So we want this to be fast, R to diffuse fast, and O to diffuse fast as well. So there is a diffusion limit here that sort of controls the total current I. So we'll do the math. You'll see in a second how it works out. But this is the basic physics picture. All right. So the thing is that in this case, you can immediately see that you can get into big trouble very soon, because as the concentration is getting depleted with a certain square root of dt, the gradient will gradually become smaller. Remember the one-dimensional diffusion limit, and therefore the flux will become smaller and smaller. Similarly, and to add to that trouble, is that the oxidized products will also not diffuse fast enough, right? It will go as square root of dt. So initially it will be a fast diffusion, but it will gradually slow down. So as a result, what will happen that this reaction will saturate very quickly with a tiny amount of current. You know, in typical structures, you can only have probably a picoamp of current. So it's not really very high. What can you do to beat it? How do you beat diffusion? Well, here is a trick that I found is sort of very beautiful. So we still have the bottom electrode just like this one, where our reduced species gets oxidized, which is fine, the same one. But now I have added a second electrode with two little gaps here. The reference electrode is not shown. That's somewhere else. But that's essential really for this circuit to complete. So now assume the same molecule has come in. The same reduced species has come in. And on this bottom electrode, it has become oxidized. So this pink is the oxidized one. Now, when the pink goes to the other electrode converts it right back. And so therefore, it goes from oxidized to reduced. So it takes the pink molecule and makes it green. Now you can see how things will build up. The green will come to the bottom electrode, it will be converted to pink, and this oscillation will go back and forth. Until, of course, the original molecule escapes from another scapegoat. So now you can see, previously I had just one reaction and corresponding to that I had one current. Generally, this current is on the order of a femtoamp or so. For typical gaps, it will be like a femtoamp. Now, because of this constant shuttling back and forth, see how many times the green molecule has come on the bottom surface. Here I have shown 3. Typically, it's on the order of for micron-sized sensors. And this gap is, by the way, on the order of 50 nanometer. That's where the Nanogap Amperometry comes in. And only nanotechnology can allow this type of gaps to be fabricated. You see, now this one can be as high as 400 to 1,000. So the signal has just been amplified 1,000 times because you have beat the diffusion limit. And you can see this in a schematic picture like this. So this is my original electrode on the left, R2O, and this is the new electrode which sort of brings things back. And you can see that there is a diffusion front going on for the green, but this is clamped to W. It cannot keep going on because as soon as the red molecule comes here, or the pink molecules, they will be converted back to green. So this concentration never changes, and as a result, the flux always remains very high. Also, for the pink one, you see, the concentration never changes because as soon as it comes here, it will immediately convert it to green. So you can see that this will have a tremendous amount of amplification compared to the other structure. So this is a recycling, of course. If you're thinking about plant and animal, we constantly do this recycling. Not at the nanogap, of course, but the oxygen and carbon dioxide, the exchange between animals and plants. Essentially, you can think about this cycling going on. So what will be the enhancement? Well, you can see in here, if it were sort of a parallel plate electrode, in that case, the current would be reducing as a square root of d naught t. Even if square root, and therefore the current will essentially saturate. It will be a very small value of current. In contrast, in here, the concentration is held fixed at a distance W, and if W is significantly smaller than square root of dt, then you can have a significant amplification. As I mentioned, that if the standard one has about a picoamp, this green one with cycling can have tens of nanoamps, and therefore this has the ability to detect concentration which are far lower than compared to the other case. So let's do some quick math to see, because we need things quantitative a little bit. So this reaction redox current here is related to the flux that is going into this electrode. How do I calculate it? The slope of this line is rho AR. A is this concentration at this point for the green. Rho BR is the concentration on the other side. Divide by W, that gives me the slope. D is the diffusion coefficient, A is the area of the electrode, and Q is the charge. So that gives me the total amount of flux that is diffusing towards the electrode. And similarly, the amount of pink molecules that are diffusing to the other electrode from A to B is given by a almost mirror-like formula, except the concentration positions have been exchanged. Now, once I know the concentration of the pink molecule and this electrode, electrode A, and the green molecules on electrode A, then I can use the Butler-Volmar equation to know how much current will be flowing. And similarly, in B, once I know the pink and green electrode, I can correspondingly calculate how much current will be flowing through electrode B. And this would be the corresponding Butler-Volmar equation, this time for electrode B. Now take a quick look. This F, the F is given by the Faraday constant divided by RT. RT is a universal gas constant. Eta A is the electrode, the voltage applied to the electrode A. And eta B is the voltage applied to electrode B, and E naught is the corresponding formal potential at which the reaction begins. So therefore, all these things can be found in any handbook. So you can put the corresponding value in for a given electrode and solve these four equations, four unknown, four equations, and I'll show you what the result is. So if you essentially solve the four equations, the final result will be something like this. So you can see that most of them are actually constants, because these are voltage. Eta A is the voltage applied to electrode A, eta B voltage applied to electrode B. So most of these things are constant. We can forget about it. Only thing I should look at is the maximum current that I can have, the limiting current. And you can see it's immediately obvious what this is, that this is inversely proportional to W. As you make things smaller and smaller, you can have more and more recycling, and so therefore your current would be larger and larger. That's one. And there's also a diffusion limit between these two. D over W is essentially the diffusion equivalent capacitance. You may remember this from the first set of lectures. And so we'll be using the same formulation here. And so that gives you a total amount of recycled current for a parallel plate planar electrode, which is good. And again, as I said, 300-400 times amplification of the current is possible. All right. So now, if your electrode were more complex, these days nobody uses parallel plate electrode. You want to have tiny nanostructured electrode with diameter on the order of maybe 10 nanometer to 20, 30, 40 nanometer. Very, very tiny electrodes. And nanotechnology, nanofabrication allows you to fabricate those structures. So in that case, only thing you have to do, you see, whatever capacitance you had, if you look at the previous expressions, you had D over W here. We'll just replace that with CDSs. As CDSs you have seen before. And so only thing that we need to do is that wherever we had diffusion current, D over W, we'll replace it as CDSs. The Butler-Volmar equation remains the same. Calculate the whole thing. See, there's only two places where things have changed. There was a D over W here. CDSs has replaced it. D over W here. CDSs have replaced it. Everything else is exactly the same. By the way, the derivation will be in the appendix, so don't worry about it. Just look at the basic formulation. So see how powerful this can be. For the CDSs for the parallel plate electrode, you simply put this diffusion equivalent capacitance in here. You will get the standard formula. There's not a problem. But even if you had two tiny nanoelectrodes like here, and you put it in the solution, very complex fluxes are going on, redox reactions are going on in the solution volume, looks very complicated. It looks like it's very difficult to solve it by any numerical method. And yet, I know what the CDSs is for two electrodes. I just looked up in Wikipedia. And A0 is the radius of this electrode. W is the separation between the electrode. D is the diffusion coefficient. And L is the length of the nanowire or the nano electrode. And all I have to do, if I wanted to know what type of current amplification I will get from this system, take the CDSs, put it in here. Done. In one shot, the entire solution, I will get one entire solution in a second. And in fact, you can show how good this is by solving the numerical and analytical result. For example, if you have a parallel plate electrode, you need to apply a certain voltage before the reaction begins, and you will have certain amount of amplification, certain current. By the way, if you didn't do this recycling, your current will be essentially unmeasurable, very small. So it has already given you amplification. However, if you do a concentric electrode, so redox reaction going on between the center electrode and the concentric surface around it, you will get significant amplification by a factor of 4 or 5. And if you do 2 nanospheres sort of, in that case, the reaction will be even faster. And so at a given voltage, depending on the voltage you want to operate it at, and to avoid parasitic reaction, if you start applying too high a voltage, there may be other reactions going on. So it's always good to operate at lower voltages. And you can see this type of nanogap amperometry with different nanostructure geometry can give you significant advantages. So here is a numerical simulation. Here are the 2 electrodes that you are seeing. Here are the redox reactions that are going on. The blue is one pole, you can sort of think about, and the red is another pole. Look at the complex flow of various diffusing and oxidizing species. And if you look at the analytical result and the numerical results in symbol and lines respectively, things are very well reproduced. A simple formula based on diffusion equivalent capacitance solves a very complicated numerical problem associated with this pair of redox electrodes. All right, so that's the first part in which we said how to beat the diffusion limit. Now let me show you very quickly then in the next few slides how to detect DNA using this. It's a new research direction and you should be able to understand it easily now. Remember the picture. The analyte came, product went out as a function of enzymes. If you didn't have any red enzymes here, there wouldn't be any reaction, right? So therefore, one way to do detection is to modulate the amount of enzyme rather than modulating the amount of analytes. Let me explain how it works. So assume that I have rotated the platinum electrode 90 degrees and these biomolecules essentially act like an enzyme, the red biomolecules. Initially on the sensor surface, you didn't have any enzyme. So there was this analytes around, but no reaction was happening. Then you have one enzyme, red enzyme landing. Then you have a bunch more landing on the sensor surface. And as they begin to land, this reaction gets initiated through the enzyme, current begins to flow, and therefore the current will now be directly proportional to the number of enzyme molecules, quote-unquote enzyme molecules, that have landed on the sensor surface. All right. Now, by the way, this enzyme molecules could be DNA, could be protein, anything that initiates the reaction. You have to choose, of course, the correct molecules, reaction molecules that will recognize this process will do. All right. So do you remember this particular equation, that of enzyme kinetics? What was the equation called? This is called a Michelson-Melton equation, and you may remember in the last lecture we discussed it, 1 over ISS. Previously we focused on the number of analyte molecules coming in. For us last time 1 over Imax was a constant, right? That was proportional to enzyme. This time around, this is our target of interest because we'll assume that there are lots of reaction molecules around. It is the enzyme molecule which is rate limiting. So we'll focus on this. Now the Imax is related to Vmax. Vmax is a maximum velocity or maximum rate. And you may remember that's proportional from the last lecture, proportional to the number of enzyme molecule and therefore proportional to the number of DNA. So the number of red DNA that are coming in is making the current ISS larger by proportion. So here is how it works. Assume in the beginning you have this same two nanogap sensor, two electrodes, both of them working, by the way. The reference electrode is somewhere else. And this chamber is already filled with reaction molecules, which wants to react on the electrode surface, but it cannot because the enzyme molecules is not present. The barrier is too high, so the reaction cannot happen. Here comes the DNA molecule. The DNA molecule comes and lands on the electrode surface. And then as a function of time, more and more DNA molecules come and land on the reaction surface. Once that happens, let's say the biomolecule which is there, the reaction molecule, green reaction molecule, already present but couldn't react before, now will start reacting. And the reaction rate will be proportional to the number of red molecules. And so therefore, by this constant cycling, you will see that there will be a significant amplification of the current that can be obtained by this structure. As I said, 300 to 400 times. In this particular example, only a factor of 3 in this cartoon. And so this is the essence of how you can have DNA detection at ultra low concentration through this redox recycling or redox cycling. All I have to do in this case, therefore, I can again write the full system expression. Butler-Volmar equation is exactly the same. Notice the concentration of the reaction molecules at electrode A. Only thing that has changed is the prefactor is enzyme dependent, or the concentration of DNA dependent. So the prefactor have changed, but everything else has remained the same. This is what allows faster reaction in the presence of a DNA. And only thing that the second electrode does is essentially recycles the product initiated by the red molecules, which in this case are DNA. So if you wanted to write out the steady state expression for DNA, then this will be equal to the number of receptors, DNA concentration, femtomolar, picomolar, rho DNA would be that concentration. You put it in. Km is already known from the reaction electrode, platinum in this case, for example. Dissociation, association and dissociation rates. These are all known. The Km values are known. And all you have to do is change the K0 value in the previous expression. Everything else is exactly the same. CDSS, everything same. Only thing that has changed, because of the DNA biomolecules have come in, the K0 has changed. And this is how you detect. So this change in the K0 gets reflected in the change in the current. So this is how you detect DNA molecules by amperometric sensors. So let me conclude. I tried to explain in the last 3 lectures that amperometric sensors are broadly used as glucose sensors, and they are very important. And it can be a sensitive monitor of analyte density and even can detect DNA, especially if you have nanogap sensors with a finite gap, or you can interdigitate them, the 2 electrodes, so that cycling can go on in the entire interdigitated structure. And that can give you huge improvement in the signal, even at very low analyte concentration. But remember that it's still, the biomolecule has to come first. That means still has a diffusion limit. Once it gets trapped into the nanogap amperometric structure, then the recycling will happen. But the molecule has to come first. And so therefore, still subject to the diffusion limit that we talked about before. Now this enzymatic reaction provides a built-in selectivity, because you see, only that reaction can be initiated which is enabled by this enzyme, or DNA in this particular case. So this gives you a very good selectivity, a topic of great interest that we'll discuss in the subsequent lectures. But it doesn't mean that it has solved all selectivity problem. If you start putting more and more voltage in the hope of getting more and more current, other molecules which are just lying around, then they can begin to react with the electrode. And if that happens, then you see your signal current will be contaminated. So the selectivity is improved, but selectivity problem is not solved in this particular case. So these are the 2 important things to remember for this amperometric sensors. So we have talked about potentiometric sensors. Now we just finished talking about amperometric sensors, that how at nanoscale things are changing dramatically. In the next set of lectures, we'll think about cantilever-based sensors, a small springboard essentially on which biomolecule will come in and change the resonant frequency. And once we have finished the cantilever, that will complete this set of 3. So until next time, take care.